Students, welcome to part D of today's class. Today I have introduced this extra part because I thought that I will do away with the first unit. Here we have two things actually, and I'll give you a rough idea about the two remaining topics from the first unit, general properties of the nucleus. So the first one is nuclear size determination. When I say nuclear size, then since we assume the nucleus to be spherical, then the only size will be its radius, because the radius will determine its volume, its area, everything. So when we say nuclear size, we mean the nuclear radius. But then students, here there is a slight confusion regarding the concept of radius of a nucleus, because it's not a body that we use in our macro world, that you measure from here to here and here to here and you get the radius, or you measure from here to here and you get the diameter, and from there you calculate the radius. The thing is different here, because this is a symbol of charges, and it's not charged and uncharged particles, of course, because we also have the neutrons. So we have the neutrons and the protons, two types of particles, and they are very closely bound, as we have already seen. And how they are bound? We know they are bound by the very strong nuclear force. Now we have already spoken a lot about this very strong force, and we saw that the force exists from here to here in this small dimension, and after that it becomes zero. So what actually here is measured is two types of radius. One is the charge radius, and another one is the potential radius. So we will be speaking about the charge radius actually. So charge radius, because you see, even if particles are till here, the effect, you know that if I have a positive charge here, its effect is slightly felt to certain distances outside, because you see that if it would have been electrostatics, if it would have been a normally different kind of a charged particle, then the effect of a charge is felt to quite a big distance, because F is proportional to 1 by r square, and obviously because of this squared term, the force will decay very soon, much sooner than r. But still it will not end where the charge ends. So it will be affected in an area surrounding this charge. So here in the nucleus too, you see, when I draw a graph like this, which we have seen earlier too, on this side, this is the distance. Suppose I say that distance r is what? R is the distance, or I say it as x. X is the distance from the center of the nucleus, like this, outwards. Then x0 means the center of the nucleus, and when I say x is equal to r, I mean the radius of the nucleus, that means at the edge. So it is seen that this is almost like this. So let me, it abruptly falls. But later it has also been seen that there is a slight deviation like this. So here we have assumed that the nucleus is spherical, but then since we cannot see it, we have to use indirect methods. It has been also found that all nuclei are not spherical. There are some which are like this and some which are like this. So this is obviously because of the Coulomb force, because you see, when there are a lot of protons, the protons will, although there is nuclear force which binds them together, the Coulomb force will try to distort them try to repel the protons each other, and so we will get this kind of a shape. So here in nuclear physics actually everything is very unclear and we can only speak of approximate things. Another point about the approximate is because we are bound by the uncertainty principle. And since the size of the particles are so small, uncertainty becomes very obvious here. For a big particle, for a big object like this, whether if it is moved by a very small distance, it doesn't at all matter. But for particles which are so small, a little distance means a lot, and so we have these are quantum mechanical particles obeying the uncertainty principle. So here what a most common, acceptable method for measuring of potential charge radius is the electron scattering experiment. So electron scattering experiment. So here what is done is that electrons are directed towards the nucleus, and then by how much it gets scattered, that is seen. And do we know what is scattering? Scattering is if a particle comes like this and it hits this one, then after that it goes this way. But then even without hitting, if this is a positively charged body and this is another positively charged body, if I direct this positively charged, the small one towards this, what will happen is that it will not go like this, it will go this way. So the path gets changed, deviated, and we say that this has scattered this small particle. So this is also scattering. So this is in case of very small particles, scattering is a very complex phenomenon, because here a particle in motion is equivalent to a traveling wave, which we call the matter wave. So here comes in the quantum wave theory. So we have quite some complex mathematics involved, which is beyond the scope of your syllabus in BSc, but still I'll try to give you an idea of what it is. So we will look at the experimental method which was done at Stanford University, United States of America. So this is the diagram of determination of nuclear radius. So here let's see what is happening. Here we have an electron beam coming out, and what does this electron beam do? How do I get this electron beam? I get this electron beam at quite a high velocity from something called a nuclear accelerator, which we will be seeing because it's in our syllabus. We will be learning quite a number of nuclear accelerators and what they do. So this is the electron beam. This beam comes in, it's been accelerated, and we have deflecting magnets here. Now what is a deflecting magnet? You know that a charged particle, when a magnetic field is applied, then there is a force on it, so it gets curved like this. So it is in the circular path, it comes like this. Then we have slits. Why do we have these slits? These slits has the function of collimating it into a fine beam, because you see students, however small I have an opening, let us consider for example light. It comes out like this, it comes out like this, and afterwards as you move to distance, this becomes broad. So the function of the collimator is to make this beam, keep this beam thin from the beginning to the end. That means they have to be very directed, because you see here, even if you directed it this way, it got spread out in this portion. So what is done here is that, suppose this is electron, as we have told electron, if I make a series of plates like this, which are kept at negative potential, then what will happen? If there was a tendency of the beam to spread out like this, when they enter the region inside this in this opening in the negatively charged particle, they will be repelled, and so they will be forced to move in a line. So that is how collimation is done. So that is, we learn these things when we study particle accelerators. And then we have another pair of deflecting magnets, and they reach a chamber where we have a material where this electron beam is targeted. And after that we have a spectrometer and magnetic spectrometer, by which you can measure by what angle the scattering has been how much. That means, suppose I have something like this and I want to scatter something, it comes like this. So since it's a beam of electrons, not one electron, so definitely all of them will not be scattered along the same path. Some will be this way, some that way, some this way. So that way, if this is my original path, so this angle will determine by what angle it has been scattered. So these are different angles through which it has been scattered. So, and what the spectrometer does here is, it finds out by how much you what portion of the scattered beam is being found after being scattered. And after that, by using the scattering theory in quantum mechanics, we find the scattering cross section. There's something called the scattering cross section. We will come to know about it when we study nuclear reactions. So combining all these, we will arrive at a relation between the number of particles that has been scattered and the angle by which it has been scattered. So that means 30 degree, how many has scattered, how been scattered, and all these things. And we will plot a graph in our experiment. Not we actually, this has been done by Hofstadler, someone called Hofstadler, a scientist, and his team, and they have done in the Stanford laboratory. And so what they do is, they draw a graph, and comparing this graph, they get this kind of graphs for different beams at different angles. And after that, what is done is that, comparing this with the theoretical value of scattering, a somewhat approximate result is obtained. Now this seems very vague, isn't it? That how can one find the radius of a nucleus by such a vague method? But by repeating this experiment several times, the radius of a nucleus is found to be 1.3 Fermi. So actually it is 1.3 Fermi. So we have already seen that radius is equal to r naught a to the power 1 by 3, and we know what is r naught. It is 1.3 Fermi. Fermi is 10 to the power minus 15 meters. So this is what is done. And next, the remaining thing that we have to do is the mass of a nucleus. Mass of a nucleus actually is obtained by measuring the mass of an atom. Mass of an atom, you subtract the number of electrons, z electrons, and you get the mass of atom, mass of the nucleus. And we look at it when we study linear accelerators and other things. But for now, from the next class, we will be going to the second unit.